Hi, welcome to lecture 2 in Introduction to Haskell Programming. We will continue looking at functions and types. Just to recall, Haskell is a programming language for describing functions, and a function description has two parts. The first part where we give the type of inputs and outputs, and the second part is a definition or rule for computing outputs from inputs. As we will see in this lecture, there are lots of complex ways in which we can define these rules for computing outputs from inputs. Just to recall, here is a simple function. Square is the name of the function, and its input type is int. Square is the name. This is the input type. This int is the output type. X star x is the rule. X is the argument name. And as we mentioned in the previous lecture, computing a function on an argument just means to replace x by 3 or 5 or whatever expression you supply as the actual argument when you call the function. Now, in this lecture, we will try to define a very simple function XOR, which we have already seen a definition for. Recall that if a and b are two Boolean values, then XOR is defined as follows. If a is false and b is false, XOR is false. If a is false and b is true, XOR is true. If a is true and b is false, XOR is true. And if a and b are both true, XOR is false. In other words, XOR is true exactly when the two inputs are different, and it's false when the two inputs are the same. And let's illustrate the multiple ways in which we can define functions in Haskell by giving various definitions for XOR. The aim here is not to memorize all these ways of defining functions, but to learn what are the various basic modes of expression in Haskell. Right? When we learn a language, we would like to see all the ways in which you can express your basic thoughts, and the basic feature in functional programming languages is to define a function. So there are multiple ways of defining functions. We are just learning the vocabulary here by means of trying to define a very simple function whose definition we have given here. So with that preamble, let's see the various definitions for XOR. The input is two values of type bool, and you want to check if exactly one of them is true. As I mentioned earlier, the type is bool, arrow, bool, arrow, bool. Because there are two inputs of type bool, you write them side by side, and there is an output of type bool, and then you insert arrows in between. In a programming language like C or Java, or even when you write it as a mathematical function, you might write it as a function of this type, and you might provide your input as XOR of a comma b equals whatever. But we do not do it that way here, and we will see why. And please wait for a couple of lectures before we get to this, before we resolve this mystery. But for now, XOR is defined as follows. What you see as the body of the function is a simple expression. It combines the input variables in multiple ways using some inbuilt functions. Right? So this is one of the simplest ways in which you can define functions. Other examples of such definitions we have already seen: square of x equals x star x, double of x equals x plus x, etc., etc. You can come up with your own functions. Power of x y equals x to the power y. Right? Though in this case you do not gain much by defining this power function, because there is an inbuilt operator for that. Or you could say power of 2 n equals 2 to the power n. Okay, this is raising 2 to the power n. You could write functions like this. These are simple expressions, and you have the name here, you have the argument name, the function name here, the argument name here, and just the body here. Okay. Okay. Here is the next way in which you can define this XOR function. Notice that I repeatedly kept telling that XOR value, XOR of AB is true if A is not equal to B, false if A equals B. This thing I can write as an expression here. If B1 equals B2, then false, else true. Right? This is another way of defining XOR. I am calling it XOR 2 because you can conveniently write all these functions in one file and test them all out. Yeah, so this is the second definition. Notice the important point here that this whole thing is an expression. If some Boolean value, then so you might want to say something like the absolute value of x. If x is greater than 0, then x, else minus x. Okay. So, this is an expression which, depending on some condition, will either give this value or that value. Okay. So, this is important to remember because if then else is a standard feature in many other programming languages, but in those programming languages it is a statement. Okay. So, the same thing you would write in a language like Java or C or some other language like this: bool XOR bool B1, bool B2, and you would say if B1 equals B2, then return false, else this is the kind of thing you would write. So, your overall function definition XOR of bool B1 and bool B2 is actually a Boolean value, and you achieve that by returning the value false and returning the value true. In Haskell, you do not have return like that because you are not trying to express some action. Here, this function XOR in a language like C or Java is a series of actions, and one of the actions you can do is to return the value false. Okay. Whereas here, this is just an expression. What is XOR B1 B2? It is false in the case that B1 equals B2, true otherwise. Okay. This is what you are trying to express, this mathematical definition. It has one value in one case and another value in another case. So, you are just, if then else is always an expression, right. So, the first part here is a Boolean expression, and these parts could be an integer or Boolean or whatever, right. So, like we saw in the example of the absolute function. So, the then and else define values, not a sequence of statements, and some of you who are in Java or C, you might have seen this expression: condition question mark expression 1 colon expression 2. That is exactly what Haskell does with its if then else. In C, if you want to do this, you would write B1 equals B2 question mark false colon true. Okay, that is a single expression in C, and you can assign this to some variable in C and Java and so on. Okay, and the same thing here. So, this whole thing is an expression, and you can assign it to, you can bind it to a name if you want to. Okay, so that's defining, that's if then else. This is a new mode of definition in Haskell. Earlier we just wrote a single expression involving some built-in functions. Of course, if then else is also a built-in construct. You use that to define a new expression. Okay, so is this the only way in which you can use if then else to define XOR? Here is another way. You could flip the conditions. Instead of saying if B1 equals true, so earlier we said if B1 equals B2 then false else true, we can just switch the two, we can switch the condition and the two cases, and you can write if B1 is not equal to B2 then true else false. Yeah, this is another way of writing the same XOR function. This is a third way of defining. But now this way of defining introduces a new aspect of Haskell. So whenever you have to write if some condition is true then return true else false, this whole thing is redundant, because if B is true, you are going to, the value of this whole expression is true. If B is false, the value of this whole expression is false. So instead you could just have written it as B, right? So because that's exactly what this if expression is doing. If B is true, then the value of the overall expression is true. If B is false, then the value of the overall expression is false. Instead you could have just called it B instead of writing B1. So in this particular function, instead of writing if B1 not equal to B2 then true else false, you could have just written XOR B1 B2 is nothing but B1 not equal to B2. Okay, this is a valid function. This is a much simpler function, this is a much simpler definition, and it's much more succinct, right? And this expresses what you want to say very clearly. XOR will return true exactly when the two inputs are false, right? So all you need to do is check whether the two inputs have XOR will return true exactly if the two inputs are different. So all you need to do is to check if the two values are different. That's all you need to do. So you just do the inequality check. XOR just amounts to the inequality check on booleans. Here is another cool feature. Instead of writing B1 not equal to B2, here this, when I write B1 not equal to B2, this thing is an operator. Other operators you have seen are plus, star, minus, etc. The caret operator for raising to a power, divides, etc. Right? This is an operator, and how do you use an operator? Operators are typically binary, and you put the operator in between the two arguments, right? So you write a plus b, you write x times y, you put the operator in between the two arguments. But earlier when we talked about integer, we noticed that there were two operators. One is divide, 8 divided by 5 will give you something like 1.6, whereas div 8,5 will give you 1. Okay, so div is a function, and functions are always specified before the arguments, right? So you say XOR B1 B2, you say square x, you say double y, you say div 8,5, mod 8,5, etc. right? Functions are always specified before the arguments, whereas operators are placed in between the arguments, typically for binary operators. And this introduces a new feature, which is that an operator can be turned into a function. By surrounding it with parentheses. Yeah, this is an important feature. So now this not equal to surrounded by parentheses, this thing is a function now. and functions are always placed before the arguments. So, you say not equal to within parenthesis b1 b2. Okay. So, this is another way of expressing the XOR function. So, earlier we expressed it as b1 not equal to b2, but now you are saying the not equal to function applied on b1 and b2. Right. Haskell operators, even infix operators, are just functions, and they can be used in the prefix manner by enclosing them in parentheses. So, for instance, star xy is the same as x star, star within parenthesis is a function, and you can apply it to x and y, and this is the same as x star y. Right. So, now that we have used this feature, we can move to a further simplification, which is that, notice this XOR 5 of b1 b2 is the same as not equal to of b1 b2. This is like saying f applied on b1 b2 is the same as g applied on b1 b2. A much more succinct way of saying this is to say that f equals g, right. So, there is no need to specify the arguments. This is a very nice feature, because even earlier I said XORing is nothing but doing the inequality check, and so why do you need to write b1 and b2? You can just write not equal to and leave it just like that. Okay, but you can't just write this would be invalid, but you can write this is valid. Yeah, because when you write not equal to without parenthesis, that is a very specific operator and it needs to come along with its arguments. But if you write it in the function form, then this is the most important takeaway here. One can write functions inside expressions without supplying all arguments. One can write functions inside expressions without supplying all arguments, and this is usually not allowed in most languages, but in functional programming languages this is the default in some sense. ML, Haskell, all these languages allow this. Yeah. So, therefore, that leads us to the next version, which is that you just write it as not equal to. XOR is nothing but the inequality check on booleans, that is it. Okay. So, what else can we do? Are there more ways of defining functions allowed to us? Yes, there are. Okay. After all, what is a function? Mathematically, function is a function f. If you want to recall the mathematical definition of a function is just a set of pairs such that for all x function from a to b, I must say, set of pairs S, let us say. Yeah, such that for all x there exists a unique y in B such that x comma y belongs to the set, or in other words, a function is nothing but a table giving a map of inputs to outputs. Right. So, it so happens that most functions that we define have some very simple expression that you can use to define the function. For instance, for XOR, we said XOR was something like XOR b1 b2 is b1 and not b2 or not b1 and b2. Right? That is a succinct way of defining the function, but what it defines is a set of pairs, inputs being mapped to outputs. Okay. So here Haskell allows you to sort of replicate this definition of a function as a set of pairs by just giving a table of input combinations being mapped to outputs, right. So here is all possible combinations of inputs. Each bool, there are two arguments, this is the first argument, that is the second argument, each is a bool. So bool, in the data type bool there are two values, true and false. So there are four combinations, false false, false true, true false, true true, and for each of those I can give a value, right. If you recall, I just gave this table, right, at the defining XOR. I said, oh, what happens if false false, it's false, false true is true, true false is true, true true is false. So this table you can exactly encode as a Haskell definition. Each line tackles different input combinations, and you have multiple lines of definition. This is what you may call a multiple lines of definitions. Or you may even call it multiple definitions, because you are defining the behavior of the XOR functions on different input combinations in each line, right. Of course, you cannot write XOR true true equals true, and then again on another line write XOR true true equals false. The Haskell compiler will complain, nor can you can't even write the same thing twice. XOR true true equals true, you cannot write it twice when you write this definition. When you write these multiple line definitions, each definition should tackle a different combination of inputs. Typically Haskell will complain about overlapping definitions. We will test these out later in the demo session. But the important point here is that you can write a definition of a function as just a table mapping input combinations to outputs, and we call this pattern matching because false and true are two patterns for bool. There are two patterns, false is one pattern, true is another pattern. We will see later that you can have much richer kind of patterns and not just single values like this. So yeah, so that is why this style of definition is called pattern matching, and we have just replicated the definition of this truth table for XOR in a Haskell definition, right. Okay. So, but it is very tedious to do this. Suppose I had an XOR function for 3 Boolean inputs and I want to say that my output will be true exactly when an odd number of them are true, right. Then with 3 Boolean inputs I have 8 lines of definition I need to give, and with 4 or 5 or whatever Booleans, I might want to say majority is a function, and I might have 6 Boolean inputs as definition, or 5 let us say. And I want majority of if 3 or more inputs are true and false otherwise. You can imagine that if I have to write an exhaustive table for this, it would require 32 rows, okay. So I need to do better, and this is hardly programming, right, you are just writing some tables, okay. So we will see more and more features. Even in pattern matching you can do better. It is not just that you can use these constant patterns, but you can actually do much better, come up with much more succinct ways of expressing functions, and let us look at some of them. Yeah, it is not always feasible to list all inputs. So for instance, Haskell allows you to do this. You might say that, okay, as long as the inputs are different, then I will output true, Otherwise, I'll output false, and for that you are saying there are two combinations in which the inputs are different: false, true, true, false. In those cases, you specify the value as true and true. In all other cases, you want to return false, and instead of explicitly writing out all other cases, you just give some b1 and b2, okay, some variable names. So, in general, when you invoke this XOR 8 function by saying XOR 8 true, false, let us say, the Haskell compiler, what it will do is, or the Haskell runtime, the Haskell engine, what it will do is, it will go through this definition line by line. It will look at the first line, false, true. It will try to compare it to the inputs here. False, true is not the same as true, false. True, false is the same as true, false. So, it will apply this definition and it will go through. But suppose I said, let me see if I can choose a different color. Suppose I said XOR 8 false, false. It will again go through the first line. False, true is not the same as false, false. True, false is not the same as false, false. But it will come to the third definition. Here it says b1, b2, and there it says false, false. This is the actual call. That is the function invocation. This is the function definition. So, the Haskell engine compares false, true against false, false. It's not the same. So, it goes to the next line of the definition. True, false is compared against false, false. Once again, the invocation doesn't match this line of the definition. So, it will go here, and there is b1, b2 here and false, false there. The point about Haskell is that any actual argument given will match a variable. Okay, so false, false will actually match the third line of the definition, and so you will return false. Similarly, XOR 8 true, true will match the third line of the definition, and once again you will get the output false. Yeah, so XOR 8 false, true matches the first definition. XOR 8 true, true matches the third definition. So, just to make it precise, when does a function call match a definition? Function call or function invocation? If argument in the definition is a constant, then the values applied in the function call must be the same constant. Like for instance, XOR 8 false, true. If the argument in the definition is a variable, so here this was XOR 8 b1, b2 equals false, then any value supplied in the function call matches and is substituted for the variable. This is the usual case, right? So therefore, as we saw here, XOR 8 true, false will match here, XOR 8 false, true will match the first line, XOR 8 true, false will match the second line, XOR 8 false, false and XOR 8 true, true will match the third line of the definition, and you will get the output false. Now, the nice thing is that it need not be all constants in one line of the definition and all variables in another line of the definition. I could do something like this also, XOR 9, which says if the first argument is false, then return whatever is the second argument, because XOR 8 false, false should be false and false, true should be true. So, you can actually say XOR 8 false, XOR 9 false B is B, XOR 9 B false is B, because XOR 9, I should say 9. Okay. So, we have covered all these cases by saying if the first argument is false, return whatever is the value of the second argument. If the second argument is false, return whatever is the value of the first argument. When would you fail these? You would go to the next third line of the definition only if it doesn't match the first two patterns. The only time when you will fail is when you call XOR 9 with true, then neither the first definition nor the second definition will match. So, it will match the third definition and it will produce the value false. Okay. Okay, so now you can mix constants and variables in the same line of a definition. Okay. What else can you do? Yeah. XOR 9 false true and XOR 9 false false will match the first definition. XOR 9 true false will match the second definition. XOR 9 true true will match the third definition. Note that XOR 9 false false technically matches the first definition as well as the second definition, but whichever definition matches first will fire. So, and the Haskell engine will try to go through it in this order, in the order of the definitions. So, when you invoke it with XOR 9 false false, it's only the first definition that will fire, okay, not the second one. Even though in this case it doesn't matter, because in both cases it will return the value false. Okay. So, here you will see that the argument B is used, okay, the argument name is B, it is used on the right hand side. The argument name is B, it is used on the right hand side, but the argument name B1, B2 are not used on the right hand side. So, there is one and it is painful if you are forced to provide names for those arguments even though you do not use it on the right hand side. So, B1 and B2 are ignored in the third definition, and for that you can actually provide underscore, okay, underscore means do not care, or in other words argument not used in the body. Okay, this if an argument is not used in the right hand side, then you just give underscore. Okay, so that's another definition. And here I have said XOR 11 of false true is true, XOR 11 of true false is true, and if for any other combination I will give false. Okay, and here is a version where yeah, so here is another version. XOR 10 false B is B, XOR 10 true B is not B. So, if the first argument is false, you just return whatever is the second argument, whereas if the first argument is true, then if the second argument is also true, you should give false. If the second argument is false, you should give true. So, it is negation of the second argument. So, you do not B. Okay. So, these are all multiple ways of defining functions using pattern matching. Okay. So, just to recap, we have seen in this lecture functions defined using simple one line expression or functions defined using pattern matching. To recall the rules about pattern matching, the most primitive form of pattern matching would enumerate all possible input combinations and give the value corresponding to each of them, but this quickly becomes unwieldy if your number of inputs is large, the number of input combinations is large. So, you can use a combination of actual constants like this, constant patterns. We will see later that not all patterns need be constant. There are patterns which have some function applied on some variables. We will see all those kinds of patterns in a few lectures down the line. But as far as bool is concerned, there are just three kinds of patterns: true, false, and just a variable which will match either true or false. And in case a pattern is not an argument is not used on the right hand side, then you will just use underscore for that. Okay. So, and the most important thing about pattern matching is that when you actually invoke a function with some actual arguments, you will try to match the first definition whose input patterns match the actual inputs that are given in the invocation. Okay. So, scanning from top to bottom, match whose input patterns Again, what does fire mean? Fire just means that or XOR 11 in this case. By the right hand side of that definition with arg1 and arg2 replacing b1 and b2 if necessary. Maybe your right hand side does not even mention b1 and b2, in which case there is no replacement. But if on the right hand side the actual patterns occur on the right hand side, then you will replace the actual arguments in the invocation, namely arg1 and arg2 instead of b1 and b2, those variables. Okay. So this concludes the second lecture of week 1. In the next lecture, we will look at more ways of defining functions. We will start with XOR, but we will also look at some more complicated functions. Thank you.